Yes, I'm sitting in a bed in a guest house because it doesn't have a very good study table. But anyway, this should be a nice little podcast that talks about new materials that are helping with harvesting water directly from the air. Desalination is very easy and we have good technology for it, but obviously, if you're far away from the coasts, then you may not benefit very easily. But if you can pull water out of the air, especially in dry deserts, then it could really be a lifesaver. So this little feature article in Science that just appeared in July 25 uh, talks briefly about this, so I'm going to make it even briefer and just take a few points. This is devices pull water out of thin air. Absorbent materials get cheaper and more efficient. So depending on the humidity levels, deserts have very low humidity. So if you want to get water out, you will have to flow through a lot of water, or you have to have material that's supremely efficient at absorbing the little humidity that's there. It's like trying to take out CO2 from air, which is, CO2 is a trace gas. So this is a device built at MIT, Massachusetts Institute of Technology, which harvests water in Death Valley, California, using the sun's heat. Death Valley is, of course, on the west coast in California. West coast is a dry state anyway, cold waters off the coast in the Pacific, and Death Valley is also very hot, so heat doesn't necessarily increase humidity in these regions, so humidity will be very low. Jumping here into the text, now, however, two classes of materials, water harvesting from air has been going on for, I have some allergy, has been going on for a while, so now that's discussed a bit, which I skipped. However, two classes of materials called hydrogels and metal organic frameworks have touched off what Evelyn Wong, a mechanical engineer at the MIT, Massachusetts Institute of Technology, calls an explosion of efforts related to atmospheric water harvesting. So metal organic frameworks we have already discussed. They are will be discussed briefly again here. The trick is to find a material that captures lots of water but rapidly frees it too. You don't want it to lock up the water. Hydrogel soft porous networks of polymer fibers, often impregnated with salts, seem to fit the bill in terms of high absorption and free release or fast release. In a June report in Nature Water, Xuanhe Zhao, a mechanical engineer at MIT, and his colleagues describe a water harvester that, thanks to a novel hydrogel, requires no external energy input at all. So it's just sitting in the desert like this without any energy source, and it's just producing water. So the team sandwiched the hydrogel, which contains lithium chloride salt, between two glass sheets. At night, water vapor enters the gel and is trapped by the salts. During the day, sunlight heats the gel and evaporates the water. The vapor condenses on the glass panels, forming droplets that trickle down and are captured. So far, the results are modest. Prototypes can produce up to 1.2 liters of water per kilogram of hydrogel per day in the dry desert air of Death Valley, California. So it's a concept demonstration which has promise. Jumping ahead, other researchers are using modest amounts of energy and dirt cheap materials to harvest much more water. For example, in a February report in Advanced Materials, Jihua Yu, I don't know how it's pronounced, sorry, Mr. Dr. Yu, a chemist at the University of Texas at Austin, and his colleagues describe a promising hydrogel made by altering cellulose, chitosan, ketosan, and starch, complex carbohydrates common in agriculture and food waste. The biomaterials have a dense structure that limits the amount of water they can store, and they tend to hold on to much of what they snag, even when heated. So you want a quick release, easy release, and it's not good if they lock it up. So U-Steam modified its hydrogel with chemical compounds known as zwitterionic groups that repel one another, stretching open the carbohydrates and making them more porous. Then the researchers added other compounds that cause the hydrogel to shrink when the heat is applied, helping to squeeze the trapped water out. Together, these changes enabled a prototype device to harvest up to 14 liters of water per kilogram of hydrogel daily. So much, order of magnitude higher than the 1.2 liters from the MIT device. For now, getting the water out still requires raising temperatures to 60 degrees C with an electric heater. However, Yashuan Zhao, a graduate student in Use Lab, says the low cost of the biomaterials means the device could be deployed along with solar panels in off-grid communities, so local solar power and emergency relief efforts can be aided with this nice device. Some of the most productive devices rely on a different kind of material, metal organic frameworks that we mentioned, and I have other podcasts on this. These porous atomic scaffolds have channels and pockets that can that can be designed to attract and store specific molecules, in this case water. Metal organic is a key word there. Although MOFs tend to hold less water than hydrogels, they can capture and release it more quickly, allowing them to go through dozens of such cycles in the time it takes hydrogels to go through one. So capturing, heating to release versus metal organic frameworks that can easily release, there are pros and cons. The key is to tailor them with alternating chemical groups that attract and repel water, says University of California, Berkeley chemist Omar Yaghi. In 2023, he and his colleagues reported an aluminum-based MOF that was cheap to make in bulk and that could wring water from desert air. In preliminary unpublished tests, Yagi says prototype devices using a tweaked version of his team's MOF can produce 200 liters of water per kilogram per day with only small amounts of added heat. So that's another order of magnitude jump. But Friesen's, jumping ahead, Friesen's own company, Source Global, is an encouraging example of the things that were discussed before, which I skipped. It has installed water-producing hydro panels which use a proprietary desiccant at more than 450 sites worldwide, mostly in remote off-grid locations. So it's a practical application that's already being commercially used and sold and used. Friesen believes costs will drop as manufacturing is scaled up, much as has happened with the solar panels and batteries. Atmospheric water harvesting will eventually be the lowest cost delivered potable water on the planet, he predicts, because you don't have to desalinate in one place and then transport it. You can locally produce it and use it. So, as I said, it's a short introduction, and I wanted to include it because these are advances that we need to track, since water stress is one of the biggest problems, especially for arid, semi-arid regions, poor countries. So water access, quantity and quality are always critical issues, and access can be physical access that may be limited or economic access. So if you produce water that's very expensive, then it may not help poor people at all. So you need affordable local solutions. Maybe local solar panels will be needed, but experimenting to see the capabilities, to demonstrate the capabilities, and doing scale up technological readiness level, etc., are very critical. Okay.